Good evening everyone. Today's lecture is about Bose-Einstein Distribution Law. In this law we will derive at a mathematical formula in which the distribution of particle is related with the corresponding energies, and you know that we have studied about the basic assumptions of Bose-Einstein statistics. So here we will derive mathematical relationships. So let us first try to understand the basic approach that we have to follow in all these three types of statistics, that is our classical statistics and the quantum statistics, that is Bose-Einstein statistics and Fermi-Dirac statistics. So the basic approaches in all the three types of statistics we have to follow. So first and the foremost approach we have to follow is to find the equilibrium state of a system. That is, the mathematical condition is derivative of logarithm w is equals to 0, where w denotes the thermodynamical probability of the system. So first, the equilibrium state means the state which corresponds to the maximum thermodynamical probability. That is, the value of w gets maximized. Hence, the derivative of w is equals to 0. So we take the logarithm of w. Why? Because w is the thermodynamical probability, and for a system, that is Bose-Einstein system, this value of w is very large. So instead of considering derivative of w, we consider the derivative of logarithm of w. Hence we know that this is a number and the derivative of this number is going to be equal to 0 obviously. The second condition that we have to follow is the condition for number of particles of the system. So as you know that number of particles in a system, isolated system, we consider generally is constant. Hence the derivative of the total number of particles will obviously be 0. This is the second approach that we have to follow. Third, the total energy of the system. The condition of the total energy. Consider the N1, N2 and Nk particles corresponding to the first, second and kth compartment. Then an epsilon 1, epsilon 2 and epsilon k are the corresponding energies of the particle. Then the total energy of the system is given by summation of I is equals to 1 to k. That is the total number of particles. So Ni into epsilon I is equals to constant. Total energy is constant. Hence the derivative of this total energy will obviously be equals to 0. So next, what we have to do, next step is combine all these three equations by multiplying equation second with minus alpha, where alpha is an arbitrary constant, and the equation 3 by minus beta. Beta, you know that statistical temperature, that is its value is 1 by kT, and adding in this equation first equation is, that is the derivative of logarithm w is equals to 0. Then we get a combined equation, that is derivative of logarithm w minus alpha summation of I is equals to 1 to k dni minus beta summation of I is equals to 1 to k epsilon I dni is equals to 0. This is the basic equation used in all types of statistics. Means in all types of statistics, first we will find the logarithm of w, means thermodynamical probability, most probable state corresponding to. Then we will take its derivative. Then the condition on its total number of particles and total energy. Then we will sum all these three equations and will equate it to 0. And this is the prime equation that we have to solve in all these types of statistics. So here our basic work is just to find solution of this equation, just to solve this equation. So let us start with our distribution law. So remember, first we will find the logarithm of w, then we will find the total number of particles, total energy, and then we will find a equation. So let us start the Bose-Einstein distribution law. Bose-Einstein distribution law. So let us consider we have total number of particles n, that is the sum of n1 plus n2 plus n3 is equals to plus nk. The total particles, which is constant, and total energy as we have discussed is this. And consider G1, G2, G3 and Gk are the corresponding degeneracies of the energy levels epsilon 1, epsilon 2 and epsilon k respectively. So be very clear. Degeneracy simply means that the equal energy states. Means simply just make it clear with the diagram. Suppose we have epsilon 1 energy state, and in this energy states we have Gi equally energized compartments. Means the degeneracies, Gi subcells have this much amount of energy. Means this epsilon I energy state is Gi times degenerate. This simply means, the meaning of degeneracy simply means epsilon I energy states Gi cells. So now we will find the distribution, most probable distribution for this type of system. So let us consider that. Now let us consider the distribution of Gi cells. So we know that we have Gi degeneracies of this energy state, and Ni is the total number of particles, and we have to arrange the Ni number of particles in these Gi cells. So how these can be distributed? So let us find. We know that Gi cells can be distributed. Gi cells can be distributed in how many ways? Gi ways. Simply, if you have 5 cells, then how many ways to distribute these cells is 5 ways. You have 5 ways. If 10 cells, then you have 10 ways. So if we have Gi cells, then we have Gi ways of distribution of these cells. Now we left with Gi minus 1 cells and Ni particles. How many ways of arrangements of Ni particles into Gi minus 1 cells? Because Gi cells are already distributed, so we left with Gi minus 1 cell. One cell is distributed in one way, only and only one way. Remaining Gi minus 1 cells and Ni particles can be distributed in Ni plus Gi minus 1 factorial ways. Now the total number of arrangements is Gi cells in Gi ways into the remaining cells and the particles, that is Ni plus Gi minus 1 factorial. So as the particles are indistinguishable why? As we have learned in the basic assumptions of Bose-Einstein statistics, means the particles that follow this type of statistics are indistinguishable, identical of integral spins, you remember. So here the particles are indistinguishable. Therefore, we left with some meaningless arrangements too. So let us find the meaningless arrangements. You know that the total number of meaningless arrangements will be Ni particles, the distribution of Ni particles among themselves will be meaningless. Why? Because these particles are indistinguishable. Hence the arrangements of themselves will be meaningless. Similarly, Gi cells arrangements among themselves will be meaningless. We also know that total number of arrangements is meaningful arrangement into meaningless arrangements. So we left with the number of meaningful arrangements. Meaningful arrangements will be total number of arrangements divided by meaningless arrangements. So we have total number of arrangements Ni plus Gi minus 1 factorial into Gi. And the total number of meaningless arrangements are Ni factorial into Gi factorial. So this is the number of meaningful arrangements. If you remember, the number of meaningful arrangements given by the term thermodynamical probability, that is W, denoted by W. So hence we are approaching towards our first equation, that is W. W is here. By solving further, Gi into Ni plus Gi minus 1 factorial into Ni factorial, Gi factorial can be written as Gi into Gi minus 1 factorial. Simply cancelling out Gi by Gi, W is Ni plus Gi minus 1 factorial divided by Ni factorial into Gi minus 1 factorial. This is for single ith particle, ith state. For n particle, for nth states, what we will do, we will just simply multiply the thermodynamical probabilities of the corresponding states, and we left with W is equals to the Ni plus Gi minus 1 factorial divided by Ni factorial into Gi minus 1 factorial. As Ni and Gi are very, very large, hence Gi minus 1 factorial can be considered as Gi factorial. So the W, the thermodynamical probability, will be Ni plus Gi factorial divided by Ni factorial into gi factorial. Next, we know that what we have to do, we just simply take the logarithm of this term w, the thermodynamical probability. We'll take the logarithm of this term. So hence, taking logarithm on both sides, we left with logarithm of w is equals to, this sign is replaced by the sign of summation. If we're taking the logarithm, multiplication sign reduced by the summation sign, you know that. So the summation of I is equals to 1 to k logarithm of ni plus gi minus 1 factorial, and this term is in the denominator, hence this term is left with the minus sign. So now you know that the Stirling formula for the logarithm of factorial term says logarithm of n factorial is equals to n log n minus n. Hence, solving further, logarithm of w is equals to summation of I is equals to 1 to k ni plus gi logarithm of ni plus gi minus ni plus gi minus of ni logarithm of ni plus ni minus of gi into logarithm of gi plus gi. Next, solving it, logarithm of w, we left with logarithm of w is equals to summation of I is equals to 1 to k ni plus gi logarithm of ni plus gi. As ni and ni got cancelled out, we're left with this equation. So for equilibrium state, you know that the most probable state or equilibrium state corresponding to the state of maximum thermodynamical probability. So if this number is maximum, then obviously the derivative of this number will be equals to 0. On further solving this equation, we're left with summation of I is equals to 1 to k dni logarithm of ni plus gi minus dni logarithm of ni is equals to 0. So hence, we left with this equation. So now you know that what we have to do. Second, we have to find the condition on the total number of particles. And we know that total number of particles are constant, as we have seen in the basic approach initially. Next, what we will do, we just multiply this equation with minus alpha and adding this equation to equation first. Next, the condition on total energy of the system is also remains same, and we will multiply this equation with minus beta, and we will then add this equation also in this equation first. You know that, as we have studied in a basic approach of these types of statistics. So let us follow these steps. We left with summation of I is equals to 1 to k logarithm of ni plus gi minus logarithm of ni into dni minus alpha summation of I is equals to 1 to k dni minus beta summation of I is equals to 1 to k epsilon I dni is equals to 0. So on solving this, so we left with summation of I is equals to 1 to k logarithm of ni plus gi minus logarithm of ni minus alpha minus beta epsilon I into dni is equals to 0. And the logarithm of ni plus gi, so this term in the bracket should be equal to 0, because total number of particles can't be 0. So this term has to be 0. So equating this term equals to 0, we left with logarithm of ni plus gi divided by ni is equals to alpha plus beta epsilon I. So on solving, ni is equals to gi divided by e raised to the power alpha into e raised to the power beta epsilon I minus 1. So ni is equals to gi divided by e raised to the power alpha into e raised to the power epsilon I by kt minus 1. Why? Just because we know that beta is nothing but the statistical temperature 1 by kt. This is our basic equation, the basic distribution law for Bose-Einstein statistics. This simply tells us how many particles corresponding to this energy state. So this is the distribution law. This gives us the knowledge about the distribution of the particles among the respective energy states. So next we will discuss about the applications of Bose-Einstein statistics, that is blackbody radiations, Planck's radiation law, Wien's displacement law, and etc. in our further lectures. So till then, thank you.